Welcome back to our aerodynamics. Uh, so let us start aerodynamics. Today we are completing 2, and let us see what is the next one it will be. We will have the what is velocity potential. We have seen the stream function. Similarly, we will talk about the what is velocity potential. Stream function we have done in detail, right? In two-dimensional flow, the same way in two-dimensional flow, consider an imaginary line O to P, that is O to P, you consider joining the line of a pair of axes, and which you consider a point P, and that one again it is the axis of X and Y only. So with that, we will resolve that one. The Q is flowing like this, X in the direction like this, in this direction. So it is how much is really the fluid is coming across the line OP, and how much line is going along the line OP. So if we again integrate from O to P, we will get it. So now today's interest is how to find the velocity potentials. Velocity potentials, we know that how much flow is flowing along the line OP. So that one only, if we will little bit, if we will enlarge it or we will consider it, the Q can be resolved into the two parts. Q sine beta either along the perpendicular line, or if first of all you draw a tangent like this, then how much the Q cos beta is going parallel to the tangent, and Q sine beta, it comes as our normal to it. So our objective is totally how much amount of the fluid is passing through the Q cos beta. That means along the line O to P. So that one you see at a point Q on the line, let the local velocity Q meet the line OP at an angle beta. Obviously, it is not the beta is always, it will be 90 degrees, need not be, right? So it can be, if it is 90 degrees, then there is no flow. In case there is a beta angle, it has some value, then we will say that there is some fluid is along the O to P is going. So how much it is there? Then the constant velocity parallel to ds is the Q cos beta. That is the simple trigonometry result. We have done it. So with this, the amount of the fluid along the ds is how much? Q is the total velocity, free stream velocity which is coming. Cos beta is the component, and ds is the distance. So that's why I made a 3 color out of it. So is it for easy understanding. The total amount of the fluid flowing along the line towards P is the sum of all such amounts. The total amount, if we will do it, we will add, then we will get the, this is the way we will get the total amount of sum along the, that means along the rope or along the line OP, the imaginary line, how much it is going. So that means how we can get it? We will get it if we will integrate from O to P, that the amount Q cos beta ds, if we will integrate, we will get the total amount along the line. So OP, if we will take the integration Q cos beta ds, we will do it. So this function is called the velocity potential of P with respect to O, and it is denoted by phi. That was denoted by psi, and that is our stream function, and velocity potential is denoted by phi. So this is very important when we will study about the source and sink. So this is important. That's why I told about this. So what is the, which is OP? OP is the line. That the OP is the line is like this, and QDS is the line. This one I have drawn it. So let me erase and so that it is more visible to you. better visibility from that. Let me erase. Okay, is it perfect? I believe. Then if we look how these both parameters are dependent or independent. Velocity potential is independent of path integration. That's what I say. Now consider the O to P one way. Another way, that means you are take a consider a point P. You can go from O through the point A, or you can go through the point B. You can go like this, or we can go like this. So what will happen? This velocity potential, we are now consider any line between O and P, and necessary conditions for what is the conditions we should have? We should for the q cos beta ds to be the velocity potential phi, is that is the value of phi, and we can say that is the value of unique. So irrespective of, if we have fixed a point, with that point it is the unique value we will get. It will not change. It is the irrespective of path. So how the velocity potential phi we can write? The velocity potential phi we can write is, if we will integrate from O to P. That means path we are not saying that which direction we are now, which not direction, which path we are following. That is q cos beta ds, and that way it is a irrespective of path integrations. The value is a unique value. It is the irrespective of path integration, and value is unique. So with this, there we have seen it, the sign convention of the stream function. It is coming from left to right is positive, right to left is negative. But in this case, sign convention, what we will have sign convention for velocity potentials, the tangential flow along a curve is the product of the local velocity components and elementary length of the curve. Now, if the velocity component is the direction of integration, it is considered as positive. In case it is in the direction of the integration, it is positive. Else it is the negative. So in this term would imply that the fluid within the circuit possesses vorticity. So what is vorticity? A new word is coming, that we will talk later. The existence of the vorticity potential must therefore be implies to zero vorticity. And this flow, that we will talk maybe the little bit later, the flow. And now other words, the flow without circulation. That means we'll talk about is a without circulation, or the flow is a irrotational flow. So velocity potential phi is a closed path of, that means when we will take a complete circle, we are taking a not a line integration, we are taking a complete path circulation and come back. That means from where you have started, come back in the same place. Okay, q cos beta ds is equal, should be the 0. It is should be the 0. Then we can say the velocity potential phi is a closed path. Closed path integration we have to do. That means if we do from here and come back, we will get the its value is 0. Okay. So what is equipotential line? There we have seen the stream line. Here we talk about the equipotential line. In the equipotential line, when we will do, consider a point P. You assume there is a point P. You consider having the velocity potential phi. You assume there we had the psi. We are having here the velocity potential phi, and phi is the integral of the flow component along the OP. And let another point you consider P1, whose velocity potential is also the phi. then what will happen? So what will happen? We know it. If we integrate from O to P or O to P1, it will remain the same. Or if I'll do O to P1, if I'll come O to P1 and P1 to P and P to O, it will become the 0. That means in case this is equal to this, that means if there is no flow between P to P1. Okay, so that's what is narrated here. Therefore, the velocity potential phi, if we will integrate from O to P if you will do, or it should be equal to OP1 is equal to is the OPP1, OPP1. That is also equal to that. So, similarly, the other points such as P2, P3 up to the Pn you consider no problem. Having the same velocity potential, there will be no flow. There will be no flow in this. So with that, we can say that is called our equipotential line. Okay. What is the characteristics of the equipotential line? So if we will look it, let me do it first. Okay. The line joining the P, P1, P2, 3 are of the same velocity potentials are called the equipotential line or the line of constant velocity. That means there is a velocity potential is same or line of constant phi, or we can call this is the line of constant phi. This line is the line of constant phi. So with this, wait, let me come back once more. One more significance. There are two values which I have not told. The significant characteristic of the equipotential line is there is a no flow in such a line. This is another this one. So these are the key points we should listen or we should concentrate. So let us talk about that. What is the, there we have seen the U and V value. Similarly, the velocity components, if we see, that one we have seen in terms of the streamline psi. Here we will see in terms of the phi. What is the value of U and V? The local velocity components are U and V, right? In that coordinates, this is called our U, and any component, if you anywhere it is there like that, it will have the two components. This is the U and this is the V and this is the resultant. So if we are having the velocity Q, then we will have the like the U and V two components. Can be written as d phi is equal to U dx plus V dy. Okay. So and the equations of continuity in two dimensions, that is again the incompressible flow. What we can write? U is equal to d phi by dx equal to 0, and that means that obviously U is equal to 0. In this direction, no flow, only along that only coming. That means on the V direction only it is there in this case. So and V direction is d phi by dy. The gradient is like that. So we are going to utilize this. Okay. Thank you very much for attending this class.
Like, share and subscribe. Hit the bell icon for more updates.